name is Andrew. I'm a theoretical physicist, grad student over at University of Washington. So I'm going to tell you a little bit today about research that I do, which is how you use black holes to study things that aren't black holes. Surprisingly, it sounds confusing, but hopefully it'll make sense as we go along. I'm going to take a minute to dedicate this talk to Stephen Hawking. You can't really get too far in black hole physics without work. So some of the stuff I'm going to talk about at the end of the talk is going to be the stuff he's done. So I'm going to start off by saying why we study theoretical physics. If you're interested in experimental physics, which is the other branch of physics, stick around for Schwa's talk. But what we is understand the universe. Okay, we're good, don't worry. Theoretical physicist, not great at technology. You should see us trying to operate a projector. It's pretty embarrassing. But what we do is understand the universe from mathematical principles. So if we can build mathematical models, we can make new predictions by just doing math, like you would in any other math class. And moreover, we want to still explain some unexplained phenomena, such as new or possibly new technologies. Now, there's a lot of things we do understand about nuclear physics, but we don't understand it from really a fundamental ground-up level. But really, at the end of the day, it's because these things are just really hard math problems. All the math that has been developed so far doesn't really answer these questions, and so we have to rely on other things. But don't worry, I'm not going to with math. I'm going to bring you black holes instead, because those are a little less boring. Because these black holes, surprisingly, can serve as toy models for those things I mentioned on a previous slide, such as nuclear physics from a really fundamental perspective, or even to explain some new technologies that are coming out. But before I tell you about black holes, I have to tell you about gravity. So we start with Newton back in the 1600s, and he really had the idea to ask, why do things fall? The Lord, he was standing under an apple tree and an apple fell on his head. And he found that the reason that this is true is because matter, which are things that have mass, like you or me, they attract each other via gravitational force. It doesn't matter how much or how little gravity you have, you still have a gravitational force. And moreover, another thing about Newton's theory of gravity that is fundamentally different from the next thing I'm about to tell you about is that space and time are non-dynamical. That means they don't move. A static thing that we move through. We move through space, we go through time, everything is hunky-dory and it behaves like you think it should. And this is a pretty good theory for a lot of reasons. For instance, it explains the elliptical orbits of the planets, kind of like this diagram I drew here. And I mean, that's really why it was developed in the first place, so that shouldn't be too much of a surprise. So things get weirder. Things get weirder when we move into the 20th century, specifically the birthday boy up here, Albert Einstein. His theory of special relativity was what really kicked off the whole gravitational revolution. It was based on two really simple principles, mainly that nothing can travel faster than light, and that physics should pretty much just be the same everywhere you look, so long as you're not accelerating. And the consequences of that are really strange. And it's mostly strange when you're moving really fast. So if you move really fast, the weird things are going to happen to space and time so that these principles are made. After a couple of years of playing around and figuring out special relativity, and with some help of some really smart mathematicians, he came up with the idea of general relativity. So this is fundamentally different from Newton's gravity because space and time are now dynamical quantities. But we kind of lump them together into one thing called four-dimensional space-time. And it is dynamical in the sense that there is a mathematical equation I can write down to tell you about how space-time moves in the presence of matter. Kind of the conventional graphic we have, but keep in mind, this fabric here is a two-dimensional thing, but when we're talking about actual gravity, we're talking about 4 dimensions, not 2. So it's kind of hard to put on a slide. But this is the basic idea. Massive objects distort space-time and cause them to move in circles, let's say. So some weird things about general relativity that I'll just touch upon right now are gravitational lensing, which just means that light bends around heavy objects. This was actually how they were able to experimentally verify general relativity back in the early 20th century. Another weird thing is gravitational time dilation, that time slows down in a gravitational field relative to an external observer. This might be going on in the movie Interstellar, Christopher Nolan. He did the black hole from Interstellar. This is another weird consequence of general relativity. The reason I'm showing this is actually, this is one of the most scientifically accurate simulations of the black hole that's ever been put in a movie. This thing right here, this kind of weird halo that we're getting, that's an example of gravitational lensing. But the light from this disk that's behind the black hole is getting distorted by the gravitational field of the black hole. It's called the twin black hole. So black hole trail, well, the regions of infinitely curved space-time that are hidden behind a horizon. And what that horizon is the point of no return, so to speak. It's behind there, the gravitational field is so concentrated, the matter is so dense that not even light can escape. And because light can't escape, that's why we call it black, because we can't see it. So there is evidence for these things. Hello? There is evidence for these things. It's not just crazy mathematical concepts. Here's some data taken by the UCLA Galactic Center Group of a bunch of stars orbiting the supermassive black hole Sagittarius A star that's at the center of the Milky Way galaxy. Pay attention to this one here. It comes down and it just swoops around really fast. And moreover, we think of it as a black hole because there's no light that's coming from here. If there was a star, we would see it emitting radiation like these stars over here. So more evidence for black holes comes from gravitational waves. So like I said, space-time is dynamical, and one way you can move is like a wave, similar to how you take that sheet and just kind of shake it and generate a wave. Same thing happens but in 4 dimensions. So what happens when you have two black holes that are orbiting each other, it will generate gravitational waves. And we can actually measure these gravitational waves on Earth amazingly. This is what led to the 2017 Nobel Prize in Physics. So as you can see here, this is data collected over at LIGO in Hanford, and another site in Livingston, Louisiana. So as these black holes are spiraling each other, you're getting some kind of generation of gravitational waves on Earth that's speeding up as the two kind of merge into each other, and then eventually they collide and become one black hole and the gravitational waves go away. Kip Thorne over here, fun fact, is the guy who actually came up with the gargantuan black hole from Interstellar, and now he's a Nobel Prize. So another thing about black holes, this is where Stephen Hawking comes in, is that they are hot. They have something called Hawking radiation, named aptly after Stephen Hawking, which is a bit complicated to really explain to you what it is right now. So I'm just going to tell you black holes have a temperature, which is kind of weird because they have a temperature when they have an entropy. And if they have a entropy, that means they have laws of thermodynamics. So the same physics that is describing your cup of beer cooling right now is the same physics that describes the black hole in some sense. Moreover, it also describes hydrodynamics, which is just a fancy word for fluid dynamics of how things like water and the gases move. So because the properties of black holes, we can actually use black holes to study how things approach thermal equilibrium. That is to say, we can study complicated thermodynamics and hydrodynamics using the physics of general relativity, thanks to Hawking and Einstein and a bunch of other people. So this is what I work on. This is one example. This is not a graph I made, it's from my professor, but we are working to extend these results. Is the application to heavy ion collisions. So you may know that on the Large Hadron Collider in Switzerland, they're smashing protons into each other and seeing what comes out. You may have heard this in the news, but you might not know that they're also smashing lead nuclei together and seeing what comes out. So like I said before, the physics of nuclear physics is very still ill understood and hard to make predictions. So we use black holes to do that. So here is actually two kind of localized black holes that are coming in and colliding together, and afterwards some weird stuff's happening and energy is distributed in some weird way. And if you can really see, there's arrows on these bottom ones here that's telling you how the energy is flowing out of the system. So this is all using general relativity, all using the physics of black holes to really make predictions about lead nuclei colliding with each other at the Large Hadron Collider. Okay, so just conclusions to reiterate some things I said. So aside from the usual astrophysical context, like what are black holes, what is their gravitational effect, they can be used as toy models for a variety of unsolved problems in physics, such as nuclear physics or even new technologies. quickly we can make these connections precise because they have properties of thermodynamics and hydrodynamics. And also, Interstellar is a much better movie than Inception. It trades pseudo-philosophical and pseudo-psychological BS for real, well-researched physics. Respect it, although it still is pretty cheesy, but I think it's better. Thank you.